So in this video I'm going to talk about the calculus of parametric equations. So the previous video we hopefully learned kind of what a parametric equation is and how to graph them and possibly manipulate them a little bit. We talked about converting from parametric to Cartesian. So in this we're going to look at the calculus. We start out with f of t and g of t, which are differentiable functions. And we're going to say that x is defined by f of t and y is defined of g of t. And we're also going to point out that y is a function of x. Or maybe we should say it like this. Y is a function of x. So as we pointed out in the other video, that you can take a set of parametric equations and possibly define them in terms of y and x. And so that's what we're saying here. That's the case with these functions. So if this is true, then we can start with a basic calculus idea like the chain rule. And we know that the derivative of y with respect to t would be equal to the derivative of y with respect to x times the derivative of x with respect to t. And that's the chain rule that hopefully you all remember from Calc 1. And so if we take that chain rule and do a little solving, we can solve for dy dx by dividing by dx dt, and we get that dy dx is equal to dy dt divided by dx dt. And of course that's dependent upon dx dt not equal to 0. Otherwise we wouldn't be able to divide it. It'd be undefined. Okay? So that's now why would we want to do that? Well, dy dx, remember, is representative slope on the graph, right? So if we're looking at a graph of parametric equations, we might be interested in when the slope is horizontal, because that would tell us some flat spots, or we might be interested in when the slope is vertical, because that would be well, when the graph is straight up and down. So, and it's easy to see from this equation here, we'll call this equation 1, when dx dt is equal to 0, we have a horizontal tangent line. And when, of course, that's still dependent on, I'm sorry, that was completely wrong. When dy dt is equal to 0, we have a horizontal tangent line, and that still is dependent on dx dt not be equal to 0, right? But also at the same time, when dx dt is equal to 0, that would cause this to be undefined, and that would give us a vertical tangent line. Of course, that also depends on dy dt not being equal to 0. So when dy dt is 0 and dx dt isn't, we have a horizontal tangent line. And when dx dt is equal to 0 and dy dt isn't, we have a vertical tangent line. And you can see that could be very valuable when we're trying to figure out the graph. And then the third thing that we might be interested in doing is talking about the second derivative. So the second derivative, if we take the second derivative, you guys hopefully remember that helps us determine concavity. So you can see again why we might want to be interested in the second derivative. In this case, the second derivative would be the second derivative of y with respect to x twice. That's what we mean by the second derivative. So if we know that the second derivative would be by taking the derivative with respect to x of the first derivative. And again, that would mean that that would be equal to the derivative of y, the derivative of dy dt with respect to t over dx dt. So here, now I want to show you an example of what I'm talking about. So, for example, we have x equals t squared and y equals t cubed minus 3t. So there's a couple of parametric equations. They're both differentiable. And we could potentially write this as in terms of y. In fact, let's do that real quick. We know that, we can write y in terms of x. So that would be, for example, the square root of x is equal to t. And that means that y is equal to t to the 3/2, y is equal to x to the 3/2 power minus 3 times the square root of x. And we know that x has to be greater than or equal to 0 because of this relationship right here. X would never be negative. So y can be written in terms of x. So now let's show that we're going to find two tangent points where, let's see, what do I have to do? Well, let's just find where it's equal to, or where it has a horizontal tangent line. So we're going to go dy dx is equal to, let's use that formula that we have up here, right? Where is it? Dy dx is equal to dy dt over dx dt, right? So dy dx is equal to dy dt divided by dx dt. And so that means we need to find out what dy dt is. So dy dt, we can do that by just taking the derivative of this guy. So that would be 3t squared minus 3. And dx dt, that would be equal to just 2t. So that means that dy over dx, or in other words, dy dx, is equal to 3t squared minus 3 all over 2t. So now we want to find out where horizontal tangent lines are. It's fairly easy to see if we factor out a 3 up here. That'd be 3 times t squared minus 1 over 2t. So, of course, now that we see that, we can see that both 1 and negative 1 would make the top equal to 0. So that means when t equals 1, there will be a horizontal tangent line. And when t equals negative 1, there will be a horizontal tangent line. Because it knows, again, neither one of those make the bottom 0. So then we can go back up to my original x and y equation. If I plug in 1, so x of 1 is equal to 1, and y of 1 is equal to 1 minus 3. Should be negative 2. So that means the point 1 comma negative 2 is a point of horizontal tangency. And remember, we also found out that t equals negative 1 would also work. So if we do, let's see, x of negative 1, well, that's just still going to be 1. And y of negative 1, that's going to be, let's see, negative 1, because t cubed would be, negative 1 cubed would be negative, yep. And then negative 3 times negative 1 would be positive 3. So that's going to be in 2. So then we have another point of horizontal tangency at 1, 2. So those are my 2 points of horizontal tangency. And then we also talked about finding a vertical tangent. So that would be when t equals 0. And I already did that for you. So when t equals 0, that would mean that x of 0 is 0, y of 0 is 0, and so therefore the point 0, 0 is a vertical point of tangency. Finally, the last thing that you should be able to do is you should be able to find a second derivative, which we're talking about concavity. So let's play that out. So the second derivative of with respect to x twice is going to be equal to, let's see, that would be the derivative of dy dx with respect to dx dt. So that's going to be equal to, so I just need to replace dy dx with what it is. So the derivative of dy dx, well, dy dx, let's see, that's up here somewhere. Where's my dy dx? We determined that dy dx was that right there. So 3 times t squared minus 1. So we're taking the derivative of that, though, remember, 3 times t squared minus 1 all over 2t. So we're taking the derivative of that, and then we just have, oh, dx dt on the bottom, which is 2t, right? dx dt was 2t, am I remember that right? Yep, dx. Okay. So let's see, let's simplify that out. If we take the derivative of that, I think what I'd do is probably change this to just divide the 2t into that, so that'd be 3/2 t minus 3 over 2t, or in other words, 3/2 t to the negative 1. That'd probably make it easier to take the derivative of it. So the derivative of that would be 3/2 plus 3/2 t to the negative 2. And of course that whole thing is still divided by 2t, right? Because of this right here. So if we divide everything by 2t, we're going to get, let's see, 3 over 4t plus 3 over 4t squared. So if we turn that back into one fraction, multiply top and bottom of that by t, we'd have 3t plus 3 over 4t squared. Okay, so let's see, did I do that correctly? No, I didn't. That should have been a cube there, shouldn't it have? That should have been a cubed, which would make that a cubed, which should make that a squared. That's much better. Okay, so that is my second derivative. Now, what does that tell us? Remember, second derivative tells us concavity. So we want to know, when is the concavity, when is it concave up, when is it concave down? So once again, we could just set it equal to 0, determine, and then, you know, when it's positive, it's going to be concave up. When it's negative, it's going to be concave down. So actually, if you look at the top is always positive, isn't it? And the bottom is going to be negative when t is negative, and is going to be positive when t is positive. So really, this is going to be greater than 0 when t is greater than 0, and it's going to be less than 0 when t is less than 0. So that tells us something about the concavity of our curve. Okay. Now, just for a visualization of this, I'm going to draw it real quick for you. You could put this in your calculator and test it for yourself, but the way this thing looks is, let's see, over 1, up 2, yeah, it looks something like this. And as we're plugging in t's from positive from negative to positive, it's going to go in this direction. So that's, of course, an imperfect drawing, but you can see what we discovered earlier, that right here there's a horizontal tangent, and that would be, you can tell the horizontal tangent line is right there at the point 1, 2, and also at the point 1, -2, which is exactly what we had said. And also you can see that vertical line of tangency right there at the point 0, 0. And so you can see how that kind of plays out in the graph. Now the points of concavity are based on t here, so it's hard to, you'd have to, I didn't take the time to figure out where t is positive and where is negative, but